All right, let's get right into it. Today we're going to walk through a really critical performance fix we recently shipped, specifically for our large transcripts. It's a classic engineering story, really. You've got a super frustratingly slow UI, a deep dive into React's guts, and, spoiler alert, a pretty clever solution that just changed everything. So let's start with a feeling I bet every single one of us has had. You're trying to highlight some text in a really long transcript, maybe something that's a couple of hours long, and the entire page just crawls. It's janky, it lags behind your mouse, and it feels completely broken. That's the exact problem we were trying to solve. And here's a look at what was happening under the hood. The very moment a user started to drag their mouse to select text, you can see the main browser thread just shoots up to 100% CPU. It's totally pegged. There's just no room for the browser to do anything else. So this wasn't just a little bit slow, it was a full-on application freeze, all from one of the most basic user interactions you can think of. So to fix this, we had to figure out what the root cause was. We had to find the villain, so to speak. And after a bit of digging, it turned out the culprit was hiding in plain sight. It was React's own reconciliation process, which, at the scale we're operating at, had become this massive performance trap. Now, here's where it gets really interesting. We were using a completely standard, by-the-book React pattern, conditional styling. But here's the kicker. On every single mouse movement event, while the user was dragging, we were updating state. And that one little state change was triggering a full reconciliation across, and I'm not kidding, tens of thousands of individual word components. Every single word had to be reevaluated, which created this huge, expensive cascade of work. And for anyone who needs a quick refresher, reconciliation is, well, it's the magic behind React. It's the process where it compares its internal idea of what the page should look like, the virtual DOM, with the actual page you see in the browser. But here's the thing. Efficient is a relative term. When you're asking it to compare 30,000 nodes, that comparison process itself becomes the bottleneck. At its core, this is what we call an ON problem. For n words in our transcript, React was forced to do n chunks of work every single time the mouse moved a pixel. Think about it like this. It's like having to reread an entire 300-page book from page 1 just to highlight one new word. That's the level of inefficiency we were up against, not to mention the insane memory churn from constantly creating these giant new virtual DOM trees over and over again. Now, to keep our UI feeling smooth and responsive, aiming for 60 frames per second, we have a total budget of about 16.6 milliseconds to do everything for a single frame. That's handling the mouse event, updating state, rendering, painting, all of it. With our old O event approach, we were just blowing past that budget on every single frame of the selection drag. And that's exactly why it felt so horribly janky. So this all led us to this huge aha moment. If React's reconciliation was the problem, what if we could just sidestep it entirely? Just for this one specific high-frequency task. And that thought led us to a much more direct, almost surgical solution. And the actual implementation is surprisingly straightforward. It's just 3 steps. First, we use useRef to get a direct, raw reference to the transcripts container element in the DOM. Second, instead of re-rendering anything, we use a quick query selector to find only the handful of words that need to change. And third, we just directly toggle their CSS classes using classlist.add or remove. React has no idea this is even happening. It just sits there, completely idle. This really visualizes the new way of thinking. All our states, what's selected, what's hovered, what's a search result, they're all just predefined classes in our CSS file. Our JavaScript's job is no longer to rebuild the UI, it's just to tell the browser, hey, put this class on that element. It's like using a scalpel instead of a sledgehammer. And let's talk about the complexity difference here, because it's huge. We fundamentally changed the problem from O of n to O of k. So instead of doing work proportional to all n words in the transcript, we're now only doing work on the k nodes that are actually being selected. And in pretty much every single real-world scenario, k is just orders of magnitude smaller than n. So the big question is, did it actually work? Well, the results weren't just an improvement, it was a night and day difference. Let's look at the numbers. So this was our before. Remember this? As soon as you started dragging your mouse, the main thread was completely pinned, 100% CPU usage. The app was, for all intents and purposes, completely frozen. And this is our after. With our new direct DOM approach, the CPU usage during that exact same user action dropped to this cool, super manageable 30 to 40%. The main thread finally had room to breathe, and the UI just felt liquid smooth. This slide right here really tells the entire story in one picture. On the left, you see that long, expensive React path. A mouse event triggers a set state, which kicks off reconciliation, which creates a virtual DOM diff, which finally commits to the real DOM. It's a long pipeline with a lot of heavy lifting. And now look at the right. That's our new path. Event, a quick query for the right nodes, a class list toggle, and done. We just completely cut out all of React's most expensive work from this critical high-frequency path. So the big lesson here isn't simply that React is slow. It's not. It's about knowing when it's appropriate to step outside of the standard playbook to get a massive performance win. So we basically distilled this whole experience into a framework for the team to use going forward. So here's the rule of thumb. This direct DOM, programmatic class approach, it's your secret weapon for high-frequency, styling-only updates that have to happen across a ton of different nodes. But for anything that actually changes the structure of the page, adding or removing elements, or for smaller component trees that aren't performance critical, you absolutely stick with the declarative power of React State. It's about using the right tool for the job.
And look, let's be real, this is a trade-off. There's no free lunch. We gained a ton of performance, but we gave up a little bit of React's beautiful simplicity. The state logic is now kind of split between your components JavaScript and your CSS files. It can be a little harder to follow, which means this is a sharp tool, you should use it, but use it carefully and only when you really, really need it.
So I'll just leave you all with this question to think about. We found this massive bottleneck and we crushed it, and it really makes you wonder, where's the next 100% CPU problem hiding in our app, just waiting for us to find it with this kind of thinking?